All right. Well, this is like my fifth attempt at trying to record this lecture. Wow. I have been having technical difficulties due to the poor internet in Monona, but I'm on campus now, so hopefully this should be better. Today we're going to talk about failure analysis. This is the third lecture in our Intro to Logic and Troubleshooting course, and let's get cracking. So we'll start again with a summary. So chapter two summary. First, we're going to go through. We're going to define a few key terms. This is always important to do. If we're going to be talking about something, it's important to have good working definitions. We're going to discuss what it means for something to fail in a technical system. We're also going to discuss what reliability is. So those are kind of related, as you can guess. Then we're going to talk about the various types of failure that can occur, mechanisms for failure, impacts on failure, and then a few metrics too we're going to talk about. So how we can actually like put a numerical value with a component and associate an actual time frame for a expected failure. All right, so technical failures. So a technical failure occurs when a system or a component of the system is not achieving the desired state or completing the proper function. So this doesn't mean a total and complete failure. It could be something just not operating correctly. Everything does fail eventually. So no matter how well manufactured the component is, if it's used regularly, if it's used continuously, it will fail. So it's only a matter of what, or rather, let's see if I can do this without being too clunky. Uh, this should be how. It's really a matter of how and when. So our responsibility is to understand why a failure occurs, and the root cause of the failure is what we're after. If we understand why a system fails or a component fails, then we can design and manufacture better components in the future. So the four types of technical failures that we're going to look at today are hardware failures. This is again when you have an actual like component of a machine. Think about anything from a gear to a bolt um, fails. Or even like an electrical system or on a circuit board, if you have a capacitor that gets blown out, or you have a resistor, or a break in the wires, or anything that's actual physical hardware. Software failures, this occurs due to bugs in the system, or incompatibilities between softwares. Systemic failures, these are introduced by humans, so this is just humans making errors. And functional failures, so this is when the system or the process just yields an undesired product. Again, even though it may be producing some product, or it may be working, you know it may be not completely limited in its capacity, but it's not outputting the desired product or rate, whatever it is you're producing. All right, so hardware failures. So on the right here, there's a picture of a pump. This is the corrosion of the blades inside of a pump, the impeller inside of a pump. So mechanical and electrical components, as we said, are subject to normal wear and tear. Physical degradation may be slowed down with preventative maintenance, but again, this is something that just happens. There's just a life cycle for everything. This obviously, this impeller on this pump should have been, you know, this should have been replaced a long time ago, or this should not have been in use for a very long time. Who knows if it was? I don't know. It's a free image on the internet. And like I said, it's impossible to prevent eventual failure, but with good maintenance and regular maintenance, we can at least limit failures or identify what systems are most likely to fail. The software failures, they are systemic and non-random, meaning they are introduced by the actual person who writes the program or writes the code, and it will happen, you know, every time. So if something is incompatible, or say you're trying to divide by zero or something like that, and I run the software again, if I have the same inputs and the same code, and I'm trying to reproduce, new outputs, it's never going to, unless I go in and physically change the code, like actually update lines of code. It won't happen. This is my terminal. This is for MATLAB. I spend a good chunk of my life debugging code, so this is something I'm very familiar with. So new updates can basically um, decrease the amount of defects, decrease the amount of bugs, but they can also introduce bugs. So say every time Windows rolls out with a new update, like a big update, like Windows 10, Windows 11, there's always, when you first use it, there's always kind of weird stuff. There's always a few bugs. And then as they hear back from their user base, they update the code and it gets cleaner and it gets smoother and everything works more. Same thing for like video games. So that's why betas are released. People release betas so they can get feedback from users and basically get a bunch of data, get hours and hours and hours of data. Um, I mean, the only way you can do that is really crowdsourcing. And then from the feedback of the users, fix the code, and basically then they actually release the full game typically. So this is called the bathtub curve, and I'm sure everybody can see why. This looks like a bathtub, right? So the failure of components, and these are well manufactured, well designed components, electrical and mechanical, follow this general trend that the bathtub curve shows. So just to show like what we're actually plotting here, this H of T, so this is a failure rate, and it's a function of time. That's what the H parentheses T means. And then this is just time on the x-axis. There's a rendition of this very similar in your book. I just made it look a little prettier. So this lambda is our random failure rate. And we're going to talk about that a little bit more coming up here. But there's three regions. There's the startup or infancy region, as the book calls it, which is kind of bizarre to me. I'll probably use startup. I kind of like that nomenclature rather than infancy period. But that's the first section here. Then once we actually get past the startup phase. We've installed it. We know it's operating well. We know it's operating correctly. This is this normal life cycle, the useful life period. This is section B. So this is really where most of our components in our machine operate for their entire lifespan. Then once it reaches its like normal or projected lifespan or wear out time, we get to this region C. And you can see that the failure rate in region C starts to go way up. We're going to talk about why that is. First, let's look at the startup period. So why do we have this high rate of failure at the very beginning, and then it kind of settles into a normal operation? Well, this is due to the fact that the manufacturing process for any component is not perfect. So even the best companies, let's say NVIDIA, for every GPU they put out, so say they make 10,000 of the same model, there will be, five, six, seven of those that actually are faulty from the assembly line. Something went wrong in their manufacturing process, and it actually produced a product that was not viable. So installing a product that's not viable, or you receiving it, this is a big, this is how you have this big chance for failure. And then also just introducing a new component into a machine during the installation process. There's a lot of room for failure here. There's a lot of like places where mistakes can be made. But once we get that installed, it settles in, and the failure rate goes down to this acceptable value of lambda. So then we'll go to section B. So this is the useful life period, and this is the smallest probability of failure. We can see that with this red curve. This is right here, lambda. The failure rate is associated with a normal operation. So if the machine and the component therefore is under normal operating conditions, there is a acceptable likelihood of failure, and that's essentially what lambda represents. And then finally, we get to the normal wear period or the wear out period. This is in C. So once components have reached or exceeded their typical lifespan, the failure is more likely to occur and increases as we continue with time past our life cycle. So the further and further out I wait past a component's life cycle, to replace that component or to do maintenance on the component, the more likely a failure is to occur. All right, so this table here just shows a few examples of different components, their life cycles, and then what's actually like the root cause of their failure. We're just going to talk about a couple of these just because they're interesting, but it's cool to kind of see the difference in the expected life cycle for some of these. So let's just look at, we have a pump seal here. And so, I mean, if we have a pump, all a pump does, I mean, everyone's used a pump in their life, but technically, and from an engineering perspective, a pump pressurizes a fluid. So basically, it increases you put in energy to increase the pressure of a fluid in order to move the fluid from one location to another. That's what a pump does. In order to keep all that fluid within some sort of body, some sort of like containment, we need seals. So anytime you have two metal components coming together, there's an O-ring or a gasket that's in there. Those need to be replaced regularly. So those wear out on the order of every 6 months to 2 years. Okay. Then we look at something like a gearbox. So a gearbox, you can also think about this as the transmission of your car. Um, so your transmission of your car, at least like old cars, we're going to use that as an example because it's just easier. Basically, there's meshing gears. And so as the gears, as you like use the car, the teeth in the gears interact with one another. You know, I have this gear pushing down on this, and it kind of rotates the other gear. But when you have contact between these two hard metal surfaces, they start to basically wear at one another. There's a fluid inside of the gearboxes that's supposed to basically help, it's supposed to lubricate and help this process, or help minimize the amount of like degradation to the gears inside of the gearbox. But it also holds all the debris. So if it's not regularly cleaned out, then there's all these like chips of metal floating around in the oil. And then you have, you know, basically increased friction between those two gears, and you have um, a positive feedback loop where it just keeps damaging the gears more and more and more as the oil gets more and more full of little pieces of debris, and then eventually you have gears wear out. So the fluid inside of a gearbox or your transmission oil needs to be changed, you know, somewhat regularly. And so that's a gearbox should last on the order of 10 to 20 years. So on the order of a life cycle of a car. Now we look at a steam turbine. So a lot of my examples will come from like power, so power generation applications, specifically nuclear power. That's my expertise. And so steam turbines, if you actually go to a power plant, I've had the opportunity to go to a few nuclear power plants and actually a few gas powered plants in one in Madison. But steam turbines are huge. The turbine house that they have at like Byron, which is a nuclear plant in Illinois, the turbine house is the size of a house. They call it a house for a reason. It's big. It's really big. And so these turbines are massive. And so what a turbine is, just to kind of put this into the context, basically how power is generated is I boil steam. I use the steam to roll a turbine. So it's got these blades in there that are kind of shaped like fan blades. And basically I push steam through, it rolls this turbine. The turbine is connected to a shaft. The shaft is connected to a magnet. The magnet rotates, and that's how I generate electricity. Simplified. But these things, because they're so well machined, and so thoughtfully designed and engineered, last about 25 to 50 years. So we have power plants operating, you know, all over the country where the turbines are, you know, older than me, older than you for sure. And so these components last a very, very long time. So if we had a power cycle here, um, and there was a failure, we detected a failure, we would go and we would look at something like the pumps before we would like assume that there's any sort of failure with the steam turbine. All right, now let's talk about reliability. So during the normal operating period, there is still a small chance of failure. This is the lambda we were talking about earlier. I have B, the little section B. This is just labeled here as normal operation. So the idea of reliability concerns the normal operation like period of a component life cycle. So this type of failure is considered statistically random, and the failure, like I said, is small but acceptable depending on the application. So, for a pump seal, we said it's okay for every 6 months to a couple years for that thing to wear out. Whereas I don't, the turbine, I don't want to see that wear out for a very long time, decades on that. Um, so the life cycle, like I said, is different for each component, different on the application. And we're going to use reliability measures to quantify the integrity of the components. So we're going to have to make a few calculations to actually quantify what it means to be reliable. So these are our metrics for reliability. I'm actually just going to skip right there. So we're going to start first with the failure rate. So we were given, we talked about the failure rate. I introduced it in that bathtub plot. This is something that's provided to us by the manufacturer. So this says that I have like one failure every 1,000 hours or something like that. It's one per some time period. So that means then the mean time to fail, MTTF, as Mattia has it in his book, I have it as just T sub F is equal to 1 over lambda. So 1 divided by whatever the failure rate will give us some time frame that we should expect. Okay, after that time frame, that's approximately when we're going to see failure. That's the mean time. And mean here just means average. Then the mean time to repair. So the mean time to repair something is a combination of different smaller time segments. So I have T sub R. This T sub R is the mean time to repair. And this considers the time it takes for us to detect that there is a problem, troubleshoot the problem. So detect that there is a problem, discover and resolve. Remember, that's what troubleshooting is. Discover and resolve the issue. Install some sort of new component or some new software, and then finally reboot. Most systems, like a power plant or even your computer, don't just go from a zero state, so turned off, to turned on like that. It doesn't work like that. There's typically a reboot time for power plants. It's on the order of hours to days. For my computer, it's on the order of 30 seconds. The mean time between failures, so I have this as MTBF, this is delta T sub B. This is the mean failure time plus the mean repair time. And then finally, availability. So this gives us a measure of how much or what's the fraction of time that a component is available. So is basically is in operation. And here I have TF, so the failure time divided by delta TB, which is equal to TF divided by TF plus TR. So if I have a component where the repair time is very quick, say let's look at the batteries from our remote control in the last example or in the last lecture, that means that this might go to zero. And if that goes to zero, that means availability is damn near one. And if I think about my remote control for my TV, the availability is like almost 100%. It's very rare that I'm unable to use my remote control for my TV because I'm troubleshooting it or I'm fixing it. However, if we think about a power plant, if I have a power plant and I have something go wrong there, say it even be a pump, it might take hours before I can get that pump fixed and get everything back in operation. All right, so now the wear out period. So after the expected life cycle of a component, failure is obviously inevitable, and it just increases in likelihood the longer we wait till after the average life cycle. And so it's recommended that we immediately perform maintenance at the recommended life cycle, and continue to monitor any components that we're using past the recommended life cycle. Um, all right, so impacts on mechanical failure. So operational conditions and failure rate. Here I chose a image from the Titan submersible, um, because this guy was just an absolute idiot and operating completely outside of um, the realm of conditions in which that submarine should be operating in. It was an absolute engineering nightmare. And he had his safety team and he had engineers on his team telling him the whole time it was bad. And he just fired him, got somebody to sign off on it. But this is an example of a very poorly, very poor. failure that occurred that didn't need to occur. It was just the machine was operating outside of, the conditions that it's actually safe for it to operate in. So if a component operates inside its normal operating conditions or the designed operating conditions, then it should follow that bathtub curve. However, if we work at conditions with extreme temperatures or extreme pressures, and our component or our machine is not designed to work like that, say it's not designed to work at negative 100 C or, close to absolute zero, negative 273 C, that would be close to absolute zero, or even at 100 C or something like that, we're more likely for something to fail if we're operating outside of the specified range of conditions that are provided by the manufacturer. So when something is designed and manufactured, they have a set of operating conditions in mind, where the component is useful. So then there's also just environmental impacts on failure rate. So different components and machines require varying environments to maintain their integrity, whether it be a lack of moisture or lack of oxygen in the air. Um, for most components that we can think of, I mean, it's fine for it to be at ambient temperatures and stuff like that. But again, extreme temperatures will cause failures. So here we have just a few things. So moisture and humidity, like I said, the presence of reactive species, and extreme temperatures. So in electronics, they are designed to work again within a specific range. So my computer, the motherboard, the GPU, it's all designed to work within some specific temperature range. But they also generate heat. So every single circuit board is again just an array of little circuit elements on a board, and the board serves as basically a platform where there's wires, and electricity runs through the wires, through the components, and as it passes through each of the components, a little bit of heat is generated. This is called joule heating. Well, if I don't remove that heat, then my computer gets super hot. I mean, like, the best computers are all, my fan is humming on mine right now. But we all, have heard the laptop fan. Better computers are water cooled or glycol cooled, or even, they have some that are housed in a sealed container. Like, I have a computer that's in a separate, I mean, you can think of it as, I guess, a box where I just spray refrigerant on it. So that's another way to cool um, a computing device. But a general rule of thumb is that for every 10 degrees C above the operating conditions, the rate of failure doubles. But we can actually quantify that and calculate that failure rate using this equation here. Let's go back to my laser pointer. So this equation here. So lambda is lambda from before, but this time, we're considering a component that's operating outside of its normal operating conditions. So lambda is equal to E raised to the power of this big E divided by KT, where big E and K are the activation energy and some constant that's provided to us from the manufacturer. And then T temperature is actually what we plug in. So these will be provided by the manufacturer. Temperature is something we plug in, and then we can calculate the failure rate for electrical components working above their specified temperature range. All right, generalized statements about failure. So here I have induced failures. So we're talking about basically three different kinds of failures. So functional failures, this occurs when an instrument is healthy but misapplied or installed incorrectly. So like I said, my expertise lies in nuclear engineering, or I guess mechanical engineering and nuclear engineering, but mechanical engineering with nuclear engineering applications. So I use a lot of nuclear power stuff for examples. I want to preface by saying nuclear power is extremely safe, and the accidents we've had in nuclear power. Well, I mean, we'll talk about the big three right now, but they are tiny in comparison to accidents at other power plants. So nuclear power is very, very, very safe. Statistically, it's the safest way to generate power, and really, it's the only way we're going to be able to power the Earth over the next 100 to 1,000 years. Okay, so a functional failure, again, it occurs when an instrument is healthy but misapplied or installed incorrectly. At 3 Mile Island, so the worst nuclear accident in the United States, which wasn't an accident, nobody was harmed. There was literally nothing happened except they built a brand new plant and then had to shut it down. So, the utility company lost hundreds of millions of dollars. This happened because a check valve. So a check valve is a valve that only allows fluid one way. It's got a gate door and it only allows fluid to pass one way and then basically it closes so that it can't go back the other way. This was installed incorrectly. So they installed a check valve backwards, so they weren't able to get fluid or coolant into the reactor, and basically this caused a meltdown. But again, everybody evacuated, everybody was fine. It was just a huge waste of resources, time, and money. Next, we're going to talk about systemic failure. So this is due to human error in design, maintenance, operation, and just a general incompetence. And this example is Chernobyl. So Chernobyl, the power plant itself, there's a few things about the design of those reactors that is just um, not they don't consider safety to be the top priority. During this period, the Soviet Union considered, saving money and putting their people at risk a little bit more important. They didn't really care about the safety. There were many things, many shortcuts that were taken, and many, basically like opportunities they had to cut costs they took. So the reason that Chernobyl ended up being Chernobyl was first incompetence. So it was a test was being run that was poorly scheduled, poorly planned. That should have been aborted mid-test, but it wasn't. They continued with the test, and they basically poisoned the reactor, is what it's called. So at that point, they should have shut everything down. But the reactor themselves in Russia or into the Soviet Union weren't in a containment building. So every single nuclear reactor in the United States is in a huge concrete containment building. There's a big one at MIT, a block from my office. Um, and they're designed so that an airplane can crash into them. Uh, there's nothing comparable to any of the reactors that are in the Soviet Union or in Russia now. So there is no containment structure. So if they have a leak or if something goes wrong, Chernobyl, there's nothing to keep all that radioactive material inside. And then finally, it's just materials. So I don't know if any of you guys saw the Chernobyl series on HBO. It's actually really good. But basically, they chose to use a cheaper material, and this cheaper material ended up accelerating the reaction inside of the reactor while they were trying to shut it down really quickly. And that caused water to boil very rapidly. And this caused a tremendous increase in pressure and eventually led to a explosion of the tank or of the reactor vessel. So this is the worst. This is absolutely worst. This is poor design, poor maintenance, poor just engineering overall. And then last, we have a common cause failure. So this is Fukushima kind of fits into this. So how Fukushima, what happened at Fukushima was avoidable. But it was also, there were multiple failures that occurred due to the backup generators being flooded. So in Japan, Fukushima, for those of you that don't know, there was a massive earthquake off the coast of Japan. The earthquake caused a tsunami, and the tsunami hit I guess, the Pacific coast, so close to us, closest to us. That coast, a tsunami hit the entire coast of Japan. There were many I think, close to 10 to a dozen or something like that along that coast in Japan at that time. Only one of them had this failure occur. And the reason that Fukushima had a failure was because they had the tsunami. Every other power plant was fine, but Fukushima had their backup generators stored in a location that was under sea level. So the backup generators got flooded. So they could not use the generators to power the pumps to provide coolant to the reactor as they shut it down. So it was this snowball effect. So one thing failed and leads to multiple failures. That's what a common cause failure is. All right, so chapter two summary. So First, failure is part of life. We're gonna fail. Things are gonna fail. Components are gonna fail. But it's our job as engineers and technicians to find the root cause and to troubleshoot and to fix the problem. So you are the hero that is going to be called upon in these types of situations. The expected failure rate of a normal component under its normal operating conditions follows that bathtub curve. And understanding why components fail, what causes the failure, the root cause, leads to an increase in reliability and availability because we can manufacture better products, better components, things that are higher in integrity that will last longer and not wear down as quickly. All right, we'll look at quiz two questions now. So this is, again, just kind of a common sense check. So failures that occur early in an instrument's life cycle are called, this name is crazy to me. So this is an infant mortality failure. I'm gonna call it a early life cycle failure or something like that. I probably won't use this nomenclature, but at the beginning of a component's life cycle, if you have a failure prior to the normal life period or the normal lifespan, so during installation or even just removing it out of the box and it's already got some sort of default, this is considered by Mattia and the old engineering regime as an infant mortality failure. Software failures, they are systemic. They decrease over time due to updates in the software. They're not random. So meaning they're bugs, they're errors within the code. So if I have a set of software that I wrote that performs some task and I feed it, some data and I run the software and it makes a mistake, if I feed that software the same data, it's going to make the same mistake, unless literally we're talking about if I built an AI or an ML, a machine learning algorithm or something like that, and incorporated that in my software, now there's a little bit of randomness that we can associate with that. But overall, not random. The mean time between failures is a measure of the reliability of a repairable piece of equipment. So this is again, it tells us, the mean time between failures was the combination of the TF. So it's TF plus TB, or TF plus TR. So failure time plus repair time. So if something, rarely fails, but it takes months to repair it, then it also, like, the reliability of that piece of equipment is also questionable versus if it's something that's a very quick repair or something that doesn't fail often. So the failure time and the time it takes to repair um, are things to be considered when we're talking about reliability. Systemic failures, this is caused by human error. Think of this is Chernobyl. So this is just people not doing their job or um, incorrectly using components, incorrectly performing maintenance. This is caused by incompetence, bad engineering, or just mistakes. I mean, sometimes people just make mistakes. That happens, absolutely. But a systemic failure, when you talk about it as in systemic, this is something that really is more of a practice issue than a single person making an issue. You're going to make mistakes. I make mistakes every day. Like I said, I try to record this lecture friggin' 4 times before I actually got it to work. Hopefully this one goes. This is number 5. But you're gonna make mistakes all the time. However, if there is a a culture that kind of promotes, cutting corners or stuff like that, that induces errors like this is called systemic. And then finally, common cause failures. So these are the things that cause other failures down the line. So if I have one component fail and multiple components rely on that single component that's failed, those components will also then fail. All right, so that's it for today. We are going to, let's see. Hold on. All right. All right, so yeah, that's it for today. Yeah, we are going to or check Brightspace assignments for week 2 are going to be up. The other lecture will be up tomorrow. Now that I've just bitten the bullet and come out into campus. And then yeah, if you guys have any questions, like I said, feel free to email me anytime. You can also actually there is that Google Voice number that I put on the syllabus, and it's also on the Brightspace page. You guys can start using that if you want to. But if you text me, obviously, like text me like you would text somebody that you've never texted before. Like I need names. I don't have all your contact information. I don't have any of your contact information. So when if you do decide to reach out to me via Google Voice, make sure you do include your name and information. Besides that, yeah, we'll see you next time. Thanks.